Welcome to The Deep Dive, your shortcut to getting informed. Today, we're really diving deep into something huge. We're exploring the chaotic, super-fast evolution of the human brain, our consciousness, and what Carl Sagan famously called the knowing human in his book, The Dragons of Eden.
Yeah, it's a fantastic book.
It really is. Our mission today is basically to piece together the story of our intelligence, how we got this brain, and why our oldest instincts still seem to call the shots so often.
And to really get a handle on how fast this all happened, you almost have to start with Sagan's brilliant framing device, the cosmic calendar.
Yes, that really puts things in scale.
It absolutely does, because when you talk about deep time, billions of years, the numbers just become meaningless, right?
Yeah.
Until you scale it down. So imagine the entire history of the universe, maybe 13.8 billion years, squeezed into just one single calendar year.
Okay.
Where do we even show up? Earth itself doesn't form until like mid-September,
Yeah.
and the explosion of intelligence, it's incredibly recent. The first Homo sapiens, we don't arrive until 10:30 p.m. on December 31st.
Wow, the last couple hours.
Exactly. And think about this. Everything that defines human culture farming, the wheel, writing, science, space travel, all of recorded history unfolds in the final minute of that cosmic year. Maybe even just the last few seconds for some things.
That speed is just mind-boggling. It means you have, 4.6 billion years of Earth history, slow biological change, and then this cognitive firework display right at the very end.
Precisely.
Which really sets up the core question Sagan tackles.
Mhm.
How did this incredibly layered, complex brain pop up so quickly? And maybe more importantly, why does our ancient programming still seem to run so much of our modern lives?
Yeah, and that leads us straight to how it happened. Evolution, driven by natural selection. Darwin and Wallace, they gave us the framework. And we have to remember, evolution isn't some guided plan. It's random, it's messy, it's often really brutal.
Right. It's more about what doesn't work dying off.
Exactly. It's the massive die-off of organisms that just aren't cutting it that paves the way for those that happen to be better adapted. Our brain is basically a living museum of survival through countless environmental challenges and, failures.
Okay, so let's unpack that museum, the architecture. Sagan uses the triune brain model, Paul MacLean's idea, which suggests our brain kind of grew in layers, right?
Right.
Sequentially, with the old bits sticking around.
That's the core idea. 3 main layers, built one on top of the other, but the older ones are still very much active. We start at the bottom, the absolute oldest part, formed hundreds of millions of years ago. The R complex, the reptilian complex.
The inner lizard.
Pretty much. It wraps around the brainstem, the midbrain. We share it with reptiles, other mammals, and its job is fundamental, primal stuff. Aggression, staking out territory, rigid social hierarchies, ritualistic behavior, non-negotiable survival functions.
So when we see things in human society, maybe like rigid corporate ladders or, I don't know, those really aggressive ritualized displays in sports, is that our R complex showing?
That's a perfect example. The R complex drives that kind of behavior. Think ritualized posturing just to show who's boss, stuff that isn't directly about finding food or shelter. It's pure status games. And the key point Sagan makes is that the newer brain systems couldn't develop without keeping these old structures. It's like how a human embryo briefly has structures that look like gill slits, echoes of our fishy past. The R complex is still running the basic operating system,
Okay, base layer.
Yeah.
Reptile instincts.
Yeah.
Then what's the middle layer, the emotional brain?
That's the organic system, sometimes called the limbic system. It developed maybe 150 million years ago, shared with other mammals. This is where raw emotion lives, fear, anger, love, bonding, sexuality.
Right.
It's also really crucial for memory, especially memory linked to smell, that powerful olfactory memory. And for long-term conditioning, if the hippocampus, a key part of the system, gets damaged, you see really severe memory problems.
So we got the instinctual reptile, the emotional mammal, and then finally the part that really makes us human, the neocortex.
Yes, the neocortex, or the cerebral cortex. It's the outer layer, the wrinkly bit. Geologically speaking, it's young, tens of millions of years old, but its growth just exploded in the last few million years of human evolution.
And this is where the thinking happens.
This is where the higher level stuff resides. Abstract thought, symbolic language, planning for the future, analysis. But here's the critical insight, the source of tension. The neocortex didn't replace the other two, it has to manage them.
A conflict.
Right. Sagan suggests that a lot of our global problems, our tendency towards aggression and conflict, even when we rationally know better, comes from this internal negotiation. The thinking neocortex is constantly trying to wrangle the emotional organic system and the primal R complex. We're rational animals pulled by these deep older tides.
That internal struggle makes a lot of sense, especially looking at history.
Well,
But let's shift to how we try to measure this intelligence. Aristotle apparently noticed our big brain-to-body size ratio. Does size really equate to smarts?
well, the brain-body weight ratio is a useful starting point. It's a rough metric, but it tells you something. Homo sapiens, we're right at the top of that chart.
Okay.
And guess who's often ranked second? Dolphins. Which kind of suggests the ratio isn't totally meaningless for cognitive ability.
Interesting.
Now look at the flip side. Those huge dinosaurs like Brachiosaurus, their brain-to-body ratio was tiny, like 10,000 times smaller than ours.
Yeah.
Big body, very little relative brain power.
Yet Sagan points out that just looking at absolute brain size within humans can be really misleading, right?
Totally misleading. You have these historical figures with massive brains, Oliver Cromwell, Lord Byron, apparently up around 2,200 grams. Huge.
Wow.
But then you have someone like Albert Einstein, whose brain was pretty average in size, and Anatole France, the writer, his was reportedly quite small, maybe 1,100 grams, like half the size of Byron's.
So a few hundred grams here or there doesn't seem to be the deciding factor.
Exactly. If that much difference mattered significantly for general intelligence, you'd expect massive cognitive gaps between people based on size alone, and we just don't see that consistently. It's clearly not just about the sheer volume.
So if size is just a rough guide, what is the human brain's advantage? It has to be something about how it's organized, its quality.
It seems to be about the incredible density of information storage. But there's a fascinating trade-off. Our brains are amazingly compact. Think about this. A modern computer chip might store about, say, 1 million bits of information per cubic centimeter.
Okay.
The human brain, estimates suggest it stores around 10 billion bits per cubic centimeter.
10 billion
Yeah.
compared to 1 million.
It's 10,000 times denser in terms of information storage. Just packed in there.
That's an incredible efficiency of space.
It is. But here's the paradox. The trade-off that maybe pushed our evolution in other directions. We're dense, but we're slow. Modern electronic computers can process information literally 10 billion times faster than our neurons can fire and communicate.
Whoa. 10,000 times denser, but 10 billion times slower.
Right. We have this fundamental speed limit, and this limitation might be exactly why the neocortex developed its specific abilities and why we eventually developed what Sagan calls extrasomatic intelligence outside the body, like tools, writing, computers.
Okay, that makes sense. Let's dive into the neocortex itself then. Its complexity, how it works, particularly the idea that the two halves, the hemispheres, do different things, lateralization.
Yeah, the split brain research by Roger Sperry was revolutionary here. It showed pretty clearly that the left hemisphere is typically dominant for tasks that happen in sequence. Language speaking, reading, writing calculation, logical analysis, it's the sequential processor.
The accountant and the lawyer side.
Kind of, yeah. And the right hemisphere seems specialized for more holistic, intuitive processing, understanding spatial relationships, recognizing patterns, especially complex ones like faces, music appreciation, geometry. It sees the whole picture at once. Silent artist, maybe?
And the weirdest part is that when the connection between them is cut, they can act like two separate minds in one head. I remember seeing that demo. A split-brain patient sees a word flashed only to their left eye, so it goes to the right hemisphere, right?
Correct.
And they could use their left hand, which is controlled by that right hemisphere, to pick out the object or even write the word, but they couldn't say what they saw.
Exactly. Because the language centers are usually in the left hemisphere, which didn't get the message. It's physically disconnected.
It's just such a clear, almost unnerving demonstration.
It really is. It makes those old philosophical ideas feel suddenly very biological. Like Plato's chariot metaphor from the Phaedrus. The soul as a chariot driver, that's the neocortex, right? Trying desperately to control these two powerful horses pulling in different directions.
The emotional mammal and the primal reptile.
Yeah. That metaphor feels startlingly real when you look at the brain structure and the split brain results. It's a built-in struggle for control.
So if the neocortex is the struggling charioteer, what specific physical changes allowed it to gain some control and develop these uniquely human skills, like complex language and tool use?
Well, look inside the neocortex itself. At the maps of the sensory and motor areas, Penfield's maps are famous for this. The amount of brain real estate dedicated to the hands, especially the opposable thumb, and to the mouth, tongue, and larynx, it's hugely disproportionate compared to, say, the back or the legs.
So The parts needed for tool making and talking got extra processing power.
Precisely. Standing upright, freeing the hands, making tools, this created pressure. Pressure for better coordination, for planning, for cooperation in hunting, and crucially, for a sophisticated way to communicate, symbolic language.
And we see evidence for language centers quite early.
Yeah, there's fossil evidence suggesting the Broca's area, a key speech center, was present in skulls of Homo habilis going back maybe 2 million years. It seems like language, tool use, and that rapid brain expansion all happen together, feeding into each other in this really dramatic evolutionary burst.
Which brings us back to a really fundamental question. Is language, this symbolic thought, the thing that makes us truly unique? Is intelligence a difference in kind between humans and other animals, or just a difference in degree? Like, are we on a completely different level, or just further along the same scale?
Sagan argues pretty strongly it's a matter of degree, not kind. The difference is more quantitative than qualitative, and there's compelling evidence. Think about the ape language studies.
Right, with chimpanzees using sign language.
Exactly. Chimps like Washoe and Lucy, they learned American Sign Language. They didn't just mimic, they built vocabularies of 100, 200 words. They used basic grammar. And, really strikingly, they invented new terms by combining signs.
Like compound words.
Yeah. Washoe famously saw a swan on a lake and signed waterbird.
Yeah.
Lucy tasted a radish for the first time, which is pretty pungent, and signed cry food or hurting bad food.
Wow. That's not just labeling, that's synthesis, metaphor. That feels like genuine abstraction.
It really does. And it's not just primates. Think about cultural learning. There's the famous story of Homo, a Japanese macaque.
Oh yeah, the monkey who washed potatoes. Yeah. Or was it wheat?
Wheat, initially. She figured out that if she tossed sandy wheat into the water, the sand would sink and the clean wheat would float. Genius.
Simple, but clever.
Right. But the crucial part is what happened next. Other young macaques saw her do it, learned it, and started doing it too. Then their mothers learned it from them. It spread through the troop not genetically but culturally, passed down. That's non-genetic information transfer. That's culture in action.
So if intelligence isn't exclusively human, and even culture isn't, then our big advantage must be how we amplify our intelligence, how we build on it using technology.
Absolutely. Technology is our ultimate extrasomatic tool, our intelligence operating outside the body. Think about computers. They are, in a way, external extensions of our neocortex.
Especially for those analytical tasks where we're naturally slow.
Exactly. They compensate beautifully for our slow processing speed, especially for those logical, sequential, left hemisphere type tasks.
And sometimes technology lets the two hemispheres work together in new ways.
That's a great point. Think about sophisticated computer graphics, maybe modeling complex molecules or visualizing theoretical physics. The analytical left hemisphere designs the program, crunches the numbers, but it's often the intuitive, pattern-recognizing right hemisphere that uses that visual output to gain genuine understanding, to see the complex geometry or the n-dimensional space.
Left brain builds the tool, right brain uses it to explore.
A perfect synergy. Which, of course, brings us to Sagan's caution. This rapid technological leap creates its own challenges. He points out how even Plato worried about the invention of writing.
Right, the argument was it would make people lazy, destroy their memory because they just rely on written records instead of remembering things themselves.
And we face a similar, or maybe much larger, version of that tension now. Our biological intelligence, our neocortex, has unleashed this incredible exponential technological growth. But our social structures, our political systems, they often seem stuck, still driven by the older, ritualistic, hierarchical impulses of the R complex.
So our technology is racing ahead, but our social wisdom, our cultural evolution is lagging way behind.
That seems to be the core challenge. Knowledge, Sagan says, is our destiny, our key to survival. But only if we can use our rational neocortex, our foresight, to manage the powerful drives of the older brains and ensure our technology serves us, rather than leading to self-destruction triggered by, some R-complex territorial dispute scaled up massively.
What a powerful synthesis. Our intelligence isn't just the neocortex. It's this constant, fragile negotiation between the ancient reptile, the emotional mammal, and the rational human, all now supercharged by the tools we built outside our own heads.
Yeah, and survival depends on strengthening the hand of the rational charioteer, using both hemispheres creatively and analytically.
Okay, so here's a final thought for you, our listeners, to chew on. Something that links the demands of that thinking neocortex right back to our basic biology. Sagan notes something interesting. Complex intellectual work, the kind the neocortex does, is incredibly energy hungry. The brain burns a lot of fuel.
It really does.
And he observed there seems to be a relationship between how much deep intellectual work someone does during the day and how much sleep they need. The implication being maybe that people doing mostly repetitive, non-analytical tasks might require less of certain kinds of deep restorative sleep. Now, what might that connection imply about the structure of our modern world where so much work is repetitive, and what could the consequences be if large parts of the population aren't regularly engaging in that demanding cognitive activity that perhaps our neocortex evolved for, or even needs for its own health and growth? Something to think about.